18.3 Glacial Erosion. Discuss the processes of glacial erosion. Identify and describe major topographic features created by glacial erosion. Glaciers are capable of great erosion. For anyone who has observed the terminus of an alpine glacier, the evidence of its erosive force is clear, figure 18.15. The release of rock material of various sizes from the ice as it melts leads to the conclusion that the ice has scraped, scoured, and torn rock from the floor and walls of the valley and carried it down valley. It should be pointed out, however, that in mountainous regions, mass wasting processes also make substantial contributions to the sediment load of a glacier. Figure 18.15 Evidence of glacial erosion. As the terminus of a glacier wastes away, it deposits large quantities of sediment. This close-up view shows the rock debris dropped by the melting ice. The glacier clearly acquired a significant quantity of rock debris as it advanced across the landscape. Photo by Michael Collier. Once rock debris is acquired by a glacier, the enormous competence of ice will not allow the debris to settle out like the load carried by a stream or by the wind. For example, notice in figure 18.12a the masses of rock exposed within the glacier as the ice melts. Indeed, as a medium of sediment transport, ice has no equal. Consequently, glaciers can carry large blocks that no other erosional agent could possibly budge. Although today's glaciers are of limited importance as erosional agents, many landscapes that were modified by the widespread glaciers of the Ice Age still reflect, to a high degree, the work of ice. How glaciers erode. Glaciers erode the land primarily in two ways, plucking and abrasion. First, as a glacier flows over a fractured bedrock surface, it loosens and lifts blocks of rock and incorporates them into the ice. This process, known as plucking, occurs when meltwater penetrates the cracks and joints of bedrock beneath a glacier and freezes. As the water expands, it exerts tremendous leverage that pries the rock loose. In this manner, sediment of all sizes becomes part of the glacier's load. The second major erosional process is abrasion, figure 18.16. As the ice and its load of rock fragments slide over bedrock, they function like sandpaper, smoothing and polishing the surface below. The pulverized rock produced by the glacial grist mill is appropriately called rock flour. So much rock flour may be produced that meltwater streams flowing out of a glacier often have the cloudy appearance of skim milk and offer visible evidence of the grinding power of ice. Lakes fed by such streams frequently have a distinctive turquoise color, figure 18.17. Figure 18.16 Glacial abrasion. Moving glacial ice, armed with sediment, acts like sandpaper, scratching and polishing rock. Photos by Michael Collier. Figure 18.17 Distinctive color caused by rock flour. Many lakes that are fed by glaciers have a distinctive turquoise color. The distinctive color occurs because the rock flour suspended in the lake reflects different parts of the visible spectrum more strongly than others. Photo by Grant/Shutterstock. When the ice at the bottom of a glacier contains large rock fragments, long scratches and grooves called glacial striations may even be gouged into the bedrock, see figure 18.16a. These linear grooves provide clues to the direction of ice flow. By mapping the striations over large areas, patterns of glacial flow can often be reconstructed. On the other hand, not all abrasive action produces striations. The rock surfaces over which the glacier moves may also become highly polished by the ice and its load of finer particles. The broad expanses of smoothly polished granite in Yosemite National Park provide an excellent example, see figure 18.16b. As is the case with other agents of erosion, the rate of glacial erosion is highly variable. This differential erosion by ice is largely controlled by four factors: 1. Rate of glacial movement, 2. Thickness of the ice, 3. Shape, abundance, and hardness of the rock fragments contained in the ice at the base of the glacier, and 4. Erodibility of the surface beneath the glacier. Variations in any or all of these factors from time to time or from place to place mean that the features, effects, and degree of landscape modification in glaciated regions can vary greatly. Landforms created by glacial erosion. The erosional effects of valley glaciers and ice sheets are quite different. A visitor to a glaciated mountain region is likely to see a sharp and angular topography. This is because as the more confined alpine glaciers move down valley, they tend to accentuate the irregularities of the mountain landscape by creating steeper canyon walls and making bold peaks even more jagged. By contrast, continental ice sheets generally override the terrain and hence subdue rather than accentuate the irregularities they encounter. Although the erosional potential of ice sheets is enormous, landforms carved by these huge ice masses usually do not inspire the same wonderment and awe as do the erosional features created by valley glaciers. Much of the rugged mountain scenery so celebrated for its majestic beauty is produced by erosion by alpine glaciers. Figure 18.18 shows a hypothetical mountain area before, during, and after glaciation. You will refer to this figure often in the following discussion. Smart figure 18.18 Erosional landforms created by alpine glaciers. The unglaciated landscape, A, is modified by valley glaciers, B. After the ice recedes, C, the terrain looks very different than it looked before glaciation. You can see several of the landforms depicted here by viewing Smart Figure Mobile Field Trip 4.14, Yosemite, Granite and Glaciers, page 118. Arrayed photo by James E. Patterson, Cirque photo by Marley Miller, Hanging Valley photo by John Warden / Superstock. Tutorial. Erosional glacial landforms. Your browser doesn't support HTML.
Back for another Smart Figure. After watching this video, you should be able to identify and describe erosional glacial landforms that occur in areas of alpine glaciation. Here's a look at an area of alpine glaciation. This is Pito Lake in the Canadian Rockies, and you can see a bunch of awesome glacial features here. You'll note the U-shaped valleys that are very prominent in this image, including some small ones that feed into the larger ones. Where those U-shaped valleys intersect, you end up getting these sort of knife-edge ridges, and you see a pointy little mountain here in the background. The lake itself is a glacial feature. Let's take a look at all of these. So the Canadian Rockies probably started off as a landscape that would look something like what you see in this picture. There would be stream-cut valleys, which have a V-shaped profile. But then the climate got colder, the valleys filled with snow, the snow packed into ice, and the ice began to flow. This made glaciers, and those glaciers eroded into the rock that they flowed over, and they carved it into new shapes. After the glaciers melted away, those shapes remained, and you can see some of them here. Here's that pointy mountain with the faceted sides. That's called a horn. The sort of amphitheater-shaped features up at the top of these small valleys are referred to as cirques, because they kind of call to mind a circus or a circle. If you find a small lake in a cirque, you might call it a tarn. If one tarn flows into another, which flows into another, that whole string of lakes is referred to as a set of pater-noster lakes. And then, of course, there's the main glacial valleys themselves, which are U-shaped. The intersection of those U-shapes can produce the knife-edge ridges known as arêtes, and where the arêtes abruptly truncate against the main glacial trough,
Glaciated valleys. A hike up a glaciated valley reveals a number of striking ice-created features. The valley itself is often a dramatic sight. Unlike streams, which create their own valleys, glaciers take the path of least resistance and follow existing stream valleys. Prior to glaciation, mountain valleys are characteristically narrow and V-shaped because streams are well above base level and are therefore downcutting, see Chapter 16. However, during glaciation, these narrow valleys are transformed as the glacier widens and deepens them, creating a U-shaped glacial trough, see Figure 18.18 and Figure 18.19. In addition to producing a broader and deeper valley, the glacier also straightens the valley. As ice flows around sharp curves, its great erosional force removes the spurs of land that extend into the valley. The results of this activity are triangular-shaped cliffs called truncated spurs. Smart Figure 18.19 A U-shaped glacial trough. Prior to glaciation, a mountain valley is typically narrow and V-shaped. During glaciation, an alpine glacier widens, deepens, and straightens the valley, creating the classic U-shape shown here. Photo by. Your browser doesn't support HTML5.
Alpine glaciers usually follow valleys that were originally narrow V-shaped stream valleys. As the glacier grows and advances, the moving ice widens and deepens the valley, which creates a U-shaped glacial trough.
The amount of glacial erosion that takes place will vary in different valleys in a mountainous area. Prior to glaciation, the mouths of tributary streams join the main valley, or trunk valley, at the elevation of the stream in that valley. During glaciation, the amount of ice flowing through the main valley can be much greater than the amount advancing down each tributary. Consequently, the valley containing the main glacier, or trunk glacier, is eroded deeper than the smaller valleys that feed it. Thus, after the ice has receded, the valleys of tributary glaciers are left standing above the main glacial trough and are termed hanging valleys, see Figure 18.18c. Rivers flowing through hanging valleys can produce spectacular waterfalls, such as those in Yosemite